talked about an application of Pn junction, that was rectifier. If you have a diode and then you connect it to an AC source, then at the output points you get some kind of a DC, not a very good DC. We talked about filtering, putting capacitor, full wave rectification and all that. This essentially used the forward bias of this diode. And there are many more applications of Pn junction, and for that specialized Pn junctions are made for those particular applications, and some of them use the reverse bias itself. You remember reverse bias and forward bias, you have this VI characteristics, amperes type, this is in milliamperes type. But then you have something called breakdown. We talked about this breakdown. So, if the reverse bias voltage is high, then you suddenly see that lot of current is going in that reverse bias direction. I also talked about the mechanism of that. If you have this Pn junction, and in this Pn junction you have this depletion region, and then in the depletion region you have electric field. If this is P side, if this is N side, the electric field is from right to left, electric field, and then you connect it to this reverse bias. So, battery negative is connected to the P side and this battery positive is connected to the N side. The minority carriers which make drift current, which make this reverse bias current, they, for example, in P side this electron is my minority carrier. So, this electron goes from this side to that side because the electric field helps it, electric field is from right to left, it helps. So, minority carriers drift because of this electric field. During this drift, during the period they are going through this electric field region, the speed increases, and if speed increases, then it is possible, if the reverse bias voltage applied is high enough, depletion region is wide enough, it is possible that speed increases so much that when it collides with a valence electron, it just knocks it out. So, these electrons, when they are going in this depletion region, they collide with valence electron, the bonded electrons, and if the speed is high, it is possible that the bonds are broken. And if that happens, you have more number of electron hole pairs, because valence electron, when this bond is broken, that goes to conduction band, and you have larger number of charge carriers, and therefore, you have more electrons, more holes there, the electric field is there, it takes these electrons in towards this N side and the holes towards P side. And these electrons may also get a lot of energy, they also can collide with the valence electrons, and this process can go on. That is the one reason of this kind of breakdown. Now, this mechanism, which is there for all moderately doped semiconductors, Pn junctions, is known as avalanche breakdown. So, this is known as avalanche breakdown, and you can make Pn junctions so that the breakdown occurs much earlier than this, and that happens when you have highly doped Pn junctions. So, if you dope this Pn junctions with much larger concentrations, highly doped Pn junction, then what happens? Then you have depletion layer is very thin. Okay, you remember that equation 1 by Na plus 1 by Nd, for that depletion layer width square root of some 2 epsilon naught and so on and so forth. So, if you dope it with higher concentrations of these impurities, then the depletion layer is very thin. Say of the order of micrometers, and if the depletion region is thin and you apply a reverse bias voltage, the electric field can be very high. So, E field is high, in reverse bias condition. So, thin layer, very thin layer, depletion layer and large electric field, that gives rise to a new phenomena in which the valence bonds are broken under this electric field itself, no impact, no collision, but these electrons go to the conduction band. So, valence electrons going from valence band to conduction band, that process has got sizable probability provided this depletion layer is very thin and the electric field is high enough. Now, this new mechanism is known as Zener breakdown. This is known as Zener breakdown. Zener is a name of some an American scientist, American physicist, who studied these breakdown phenomena in insulators, and then those theories, those studies were extended to semiconductors, Pn junctions and this and that. And now this Zener breakdown is used for certain kind of applications, and the Pn junctions which use this Zener breakdown for the application, they are known as Zener diodes. The Zener diodes have slightly different symbol. So, normally we show this triangle, so that is all right, but after that you have another symbol on that, and that is you put two lines like this. So, this shows Zener diode, and the characteristic is same, looks similar Vi. If you draw this Vi graph, on the forward bias side it is like this usual Pn junction, and reverse bias also it is like a usual Pn junction, but then it goes to this breakdown region. This is known as Zener breakdown. Okay. So, this voltage here is the Zener breakdown voltage, and it is sharply defined. This Vz is sharply defined. In avalanche breakdown you still have some width in this region, but here it is almost very sharply defined, and the current increases almost without increasing the voltage almost. So, that is the kind of characteristic. So, that is known as Zener diode. So, what is the use of it? Where can I apply that? The one application is that it can carry different amount of currents for the same voltage across it, and therefore, it can be used as a voltage regulator. So, voltage regulator is one use, voltage regulator. Suppose you have a very simple circuit, you have power supply, you have some power supply and that power supply is giving DC, but then DC is fluctuating. We saw if I just put a Pn junction diode to rectify and get a DC supply, even if it is a full wave rectification, even if we put capacitors, you still have some fluctuations. So, this is a DC power supply, but then this voltage source here is had some fluctuations. So, let us say these points are A and B, this is A and B, and then you have the voltage V A with respect to this B point, this we will take V equal to 0. So, this V A has some fluctuation, it is DC, right. So, as a function of time it is constant, but there is some fluctuation. And then I need a constant voltage to my appliance. So, my appliance needs a fixed voltage. So, what I do? I can put the appliance here, and this needs a constant voltage, and what I will do is I just connect it here, and then I put a resistance out here known as shunt resistance or RS, and then I put this Zener diode in reverse bias condition, and say this whole thing is my supply now. This whole thing is my supply, and from here I am taking another this output, and that goes here. So, this is one point, this is one point, and that is connected to the circuit. Generally people call this load resistance, the external resistance that you apply, that is generally people call it load resistance. So, this is, let us say this is the circuit. Now, what happens? Let us put some values also. So, let us say that what you need is, let us say the Zener diode, the characteristic is here, and let us say this is 5 volts. The diodes are made to have a particular breakdown, Zener breakdown values, that depends on how much concentrations you are putting in P side, how much concentration you are putting in N side, and so on. So, one can make it for whatever 2 volts, 3 volts, 2.4 volts, 5 volts, 6 volts, 100 volts. So, that can be made. Then each diode will have some rated watts, so that the total energy which is dissipated there, that should not be more than that particular power wattage that is given. So, maybe let us say a Zener diode is there, and that has the rating 5 volts for the breakdown, and let us say 2 watts as the power rating. What is power rating? Do not dissipate more than 2 watt in the power, otherwise the thermal heat generated, thermal energy generated will be more than what this diode can tolerate, and it may get damaged. So, that is the rating, and that rating is given in watts, and the breakdown is of course in volts. So, let us say we have this kind of thing, and what we need is a constant supply here. So, and the source here is giving me, let us say the source here is giving me some voltage which is say 10 volts, normally average 10 volts, let us say this is 10 volts. So, the source is giving me 10 volts, but plus minus fluctuations. So, what will happen as a function of time if I connect this circuit? So, let us see. Let us first do an analysis where this no load is connected. So, I have this power supply which is giving me A and B, and I have connected a resistance RS, and then I have connected this diode here, the Zener diode here in reverse bias, and let us say this VA is equal to 10 volts. At some instant VA is equal to 10 volts. So, what will happen? The circuit is complete, there will be a current. So, this is giving me a current. The current will go through this resistance, and then it will go through this diode. Reverse bias, remember, so the current is going as I have shown in this arrow. So, what is the voltage across this RS? So, let us say the voltage across this is RS. So, this voltage V is equal to 0, this voltage V is equal to 10 volt, and then across the diode this voltage is 5 volt, right. So, the current is there, but the voltage is here at this 5 volt. So, across RS the current will be, the voltage will be 10 volts and minus 5 volts, and that is 5 volts. So, you can see what is the current. The current through this RS is 5 volts and then divided by whatever is the R. So, if I say that my current should not exceed this much, 2 watt is the power rating, let us say 2 watt is the power rating. So, how much should be the maximum current? How much can be the maximum current? Let us calculate that. So, if power is 2 watts and if the voltage is 5 volt, I am talking of voltage across the Zener diode, this is all for Zener diode. I can calculate current from here. P is equal to Vi, P is equal to Vi, I is equal to P by V, that is 2 watt and divided by 5 volt, which is how much? 0.4 amperes or 400 milliamperes. So, the current through the Zener at this time is 400 milliampere. So, one has to choose the value of RS so that the current does not exceed this 400 milliampere. What should be the minimum resistance that I should put there, right? Minimum resistance. Which resistance? RS. So that the current in the diode does not exceed 400 milliampere. So, what is that RS? How do I get that? Very simple. The voltage across RS is also 5 volt in this condition, right. The voltage across RS here, this is also 5 volt because this is giving me 10 volts, this 5 volt is here, the remaining 5 volt is here. So, if this is 5 volt and the current is 400 milliampere or 0.4 ampere, because I have not put any load at this moment, I am just taking unloaded circuit. So, the entire current which is there in RS, that is going through the Zener also, and therefore, it is 0.4 ampere, and you can calculate how much is RS. RS is V divided by I. So, 5 divided by 0.4 ohm, and how much is this? This is 50 by 4, 12.5 ohms. So, that is the minimum resistance that one has to put there, so that the rating, power rating is not exceeded. That is fine. So, now let me put a load here. Now, I have this RS and let us say we put it somewhere, let us say 12.5 minimum, and then of course, one should not do that, but for calculations. And then I have this diode, and then across this diode I am putting another resistance, load resistance, let us say I put 1 kilo ohm. Normally these things are done for electronic circuits where the currents are on the order of milliamperes, few tens of milliamperes maximum, and therefore, the resistance are often in this range kilo ohm or so. So, let us say 1 kilo ohm, and let us say here it is 10 volts. From this side it is coming at this moment, let us say 10 volt, and this is of course 5 volt. So, what is the current now? Current through this RS, current through this Zener, and current through this 1 kilo ohm. So, first let us say current through this load resistance 1 kilo ohm resistance. So, here what is the voltage? What is the voltage here? This voltage is same as this voltage, and this voltage is 5 volt. So, here the voltage is 5 volts and the resistance is 1 kilo ohm. So, what is the current? Current in load, that is going to be V by R. So, it is 5 milliampere. So, the current here is 5 milliampere. What is the current here? What is the current here? Current in RS. So, on RS the potential difference here is, potential difference between these 2 points is still 5 volts, this 10 volt and minus this 5 volt is this 5 volt. So, 5 volt is here, and therefore, this current will be I in S RS. So, let me write it IS, this current here IS, this will be 5 volts and then divided by 12.5 ohms. So, how much is this? This is 400 milliamperes. So, now you can calculate how much is the current through the diode. The current through the diode will be this 400 milliampere and minus 5 milliampere, and that will be 395 milliampere. So, when the load was not there, the current through the Zener was 400 milliampere. When the load is there, the current is 395 milliampere. So, the current has changed, but the voltage across the Zener diode remains 5 volt, and that is also the voltage across the load resistance. So, that is how the things go. Now, as you have a upper limit on the current in Zener, you also have a lower limit on the current in Zener. Why lower limit? Because in this reverse bias breakdown condition, whatever, you need a certain current here. So, you should not operate in say this region, where it is still not very constant voltage, the voltage is still increasing, decreasing with current. But if you are somewhere here at this current here in this region, here the voltage is almost fixed, and therefore, there is a minimum current also, so that you are in that safe vertical region in the this characteristics, this IV characteristics. You can similarly calculate the value of resistance. It should we had calculated the minimum resistance, and now we can also calculate the maximum resistance, so that the current does not go down and become less than this minimum needed. So, these are the kind of things which a Zener diode has, and you can make a regulated power supply. What happens if this 10 volts becomes, let us say, 8 volts? What happens to this calculation if this 10 volts becomes 8 volts? So, not a difficult task, you can always do the analysis, and let us say this is 8 volts. So, you have this supply, and the supply is, suppose at certain instant the voltage dropped from 10 volts to 8 volts, what happens? So, this is it, and then what we have is what we have here is resistance RS, which is 12.5 ohms, and then we had this diode here, 5 volt diode, and from here we had this 1 kilo ohm load. So, if this drops to 8 volt, what happens? The potential here remains 5 volts, potential here remains 5 volt. So, the current which is there in the load I L, that is still 5 volts and divided by 1 kilo ohm. It remains the same, and that current 5 milliampere will remain the same. What will change? The potential across this R S, this potential across this resistance, and this will now drop from 5 volts to 3 volts. This total is 8 volts, this is 5 volts, and therefore, the voltage across R S is now 8 minus 5, and that is 3 volts. So, now what is the current in R S? I S. I S is equal to voltage divided by resistance. Voltage is 3 volts and resistance is 12.5 ohms. So, how much is this? This is 6 by 25, 24 by 100, 0.24 ampere or 240 milliampere. See how the current has changed. And so, what is the current through this diode, Zener diode? That will be 240 milliamperes are going here, 5 milliampere is going here, the rest is going here. So, ID will be 235 milliampere. So, with voltage fluctuations, current in diode will fluctuate, current in RS will fluctuate, but the voltage will still remain 5 volt, whether it is 10 volt input or whether it is 8 volt input or it is 9 volt or 9.2 volt or 9.8 volt or 10.2 volts. The output of this which is fed to the load resistance remains 5 volts. So, that is the meaning of regulated power supply. But remember, this source voltage should be more than the breakdown voltage. If the supply voltage drops to 4 volts, then this will not work. You have to be in that reverse bias Zener breakdown region, that minimum, that whatever milliampere current is there, you should be in that region, and therefore, the source voltage should be greater than, larger than the Zener breakdown voltage. So, this is a condition. So, if it is 5 volts breakdown, then that must remain above 5 volts. It could be 7, it could be 6.8, it could 7.5, it could 10, it could 9, that can fluctuate, but as long as it is more than this Zener breakdown voltage, this regulated supply will not be disturbed. The next application, next special purpose diode I will be talking is called photodiode. So, normal Pn junction with proper concentrations of impurities, but it is photodiode in the sense that it interacts with light, photons, and therefore, in the construction you have some transparent window somewhere, so that light can enter the system and fall on that depletion region or near depletion region. So, during this fabrication, one has to make some kind of a transparent window, and then what happens? If light falls on this diode, on this Pn junction near depletion region or in the depletion region, the photon energy that creates new hole electron pairs. So, you have all those valence electrons in this valence band. That means you have electrons here, they are all bonding, they are taking part in the bonding. So, they are providing those covalent bonds, and then conduction band where you have very few number of electrons, although the levels are very much there. And then when light falls, and energy of a photon, you know, it is hc over lambda, h is Planck's constant. C is the speed of light, and lambda is wavelength. H into C turns out to be 1240 eV/nm. eV is electron volt, this is unit of energy. So, eV and nanometer. So, H into C turns out to be this. You can easily calculate how much will be the photon energy if you know the wavelength. For example, if wavelength is, let us say, 400 nanometers, then the energy of the photon will be 1240 eV/nm, and then 400 nm, and that will be 3.1 eV, 3.1 eV. If lambda is, let us say, 620 nanometers, then E will be 1240 eV/nm over 620 nanometer 2 eV, and so on. So, for visible region, when we say that lambda goes from say roughly 400 to 700 nanometers, correspondingly you can see that energy goes from, let us say, some 1.8 eV to some 3.2 eV or so, like that. So, this is the range for visible region, and band gap is less than that. Silicon, it is 1.12 electron volts. So, if light falls, photon energy is enough to take this electron from let us say here to here, because this is the band gap Eg, and if photon energy hc by lambda, if this is more than Eg, then when it falls, it is very much possible that a valence electron takes up that energy, the bond is broken, and the electron becomes free, a hole is created. So, new hole electron pairs can be created, and if new hole electron pairs are created, the current is increased if there is circuit out there. So, if you have let us say this junction, you have this junction, and then you have connected it to a battery, biased, forward biased or reverse biased. This particular figure is for reverse bias, you can also have forward bias. So, if the number of charge carriers increase, correspondingly you will have more conduction and the current will increase. You can put some resistor in between so that you do not pass very high current. It is always advisable to play safe, to limit the current, because if you pass too much of current, your Pn junction get destroyed. So, the current increases with more charge carriers created by the light falling on the junction. Now, if you do a forward biasing and then shine light on that, already there is a lot of current, because this is because of the majority carrier. In forward bias the current is because of the majority carrier and they are in majority. So, if a little bit increase is there, that will be difficult to see. But if you operate in reverse bias and the current is due to minority carriers which are much small in number, and then you shine light and new minority carriers are created together with the majority carrier, but here the current is due to minority carrier only, the increase can be really sizable, and therefore, these photodiodes are generally operated in reverse bias conditions only, and then the current is mainly because of these new electron hole pairs and therefore proportional to the intensity of the light. Okay. Intensity of the light tells me per second, per centimeter square how much energy is falling, and therefore how many photons are falling, and therefore how many electron hole pairs are created, whatever be the ratio. So, the current in that case, if you shine light here on this depletion region and you create new carriers in reverse bias, the electric field is there and that electric field takes the electrons to this side and the holes to this side, and new electron hole pairs are being created, current increases. So, this increase in current is proportional to almost to the intensity of light. And this is how this photodiode can be used as a photo detector to detect whether there is a light and to detect how much light is there, to measure the intensity of light. So, this is the application of these photodiodes, which are used as photo detectors or which are used to compare the intensity of light. Of course, the stray light can also be there. You want to measure the intensity of light coming from a small torch, but if you put off the torch, then also maybe in the room there is light and that light is falling on the Pn junction diode. So, there is some background current. So, that background current has to be subtracted, or the photodiode has to be very carefully wrapped in something, so that stray light does not go, only the light that you intend to pass, only that goes, those things are there, but nevertheless this is one device which can measure the intensity and detect the light. The next application, special purpose diode, is very common and almost everyone knows about it, and that is light emitting diode. Popularly known as LED. All those filament bulbs are now being replaced, all those CFLs, tube lights, most of them are being replaced. People are using LED lamps and LED bulbs and all those LEDs. Of course, LEDs were in use for quite some time. We had all those LED small indicators on different appliances, but in very recent years, for say a year or so or 2 years, this LED has come with a great surge. So, what is this light emitting diode? This is also diode. It is, the process is just reverse of this what we did photodiode. You have a Pn junction, and in the Pn junction all the time you have a generation of new hole electron pairs and recombinations of those hole electron pairs. So, that recombination is the key for this LED. So, recombination of recombination of electron hole pair. And that always takes place in any PN junction diode. The generation and this recombination, they always take place because of the thermal energy exchanges. But if the band gap is small, like in silicon or in germanium, if this band gap is small, if this electron here and this hole here, if they recombine and release energy, that energy is dissipated in that junction itself, like thermal energy. It is a thermal exchange. But what if this gap is comparable to the visible light photon energy, which I showed it is some 1.8 eV to some 3.2 eV or so. And if the electron and hole in such a system recombine and the energy is released, that energy can be released in the form of a photon. And that means it emits light. If once again during the fabrication, if you have a transparent cover, so that in the junction when this photon is created, that can come out, then you have this light emitting diode. So, what is this? It is always connected in a forward bias to increase that probability of recombination. In forward bias, if you have this let us say this is the junction, you have this depletion region, this is P side, this is N side, and in forward bias what happens? The diffusion current increases. Diffusion current increases means the majority carriers, they flow in great numbers. So, the holes go from this side to that side and the electrons go from this side to that side. And when holes go from this side to that side, the holes reach here, these positions, here they are minority carriers, and there are a lot of electrons. In this side there are a lot of electrons. It is full of conduction electrons. This is N side, doped. So, you have a lot of them. So, this minority carriers which are injected here because of this forward bias, they will have enough probability to combine with these electrons, because there are so many electrons, and create that recombination and create that photons, and the light will be emitted. Similarly, the electrons which are coming on the other side, the electrons which are coming here, these electrons are reaching here, right. So, this is known as minority carrier injection, because in this side, in this P side, these electrons are minority carriers and they are injected here near the junction edge in large numbers. But then you have lot many holes. This is P side. So, we have doped it in such a way that you have lots of holes here, and therefore, these electrons which reach here will have a good probability of combining with some hole and create that photon. So, the light emitting diodes are operated in forward biased region. The basic thing is this gap should be, this Eg, this gap should be in the visible range. This Eg should be in that range 1.8 eV, 3.2 or 3.4 eV. So, that visible range, how do we achieve that? And that is the place where lot of research had been done, and people have come out with materials which can give energies in this particular range. And the basic material there is this gallium and let us say the gallium arsenic combinations. So, gallium arsenic together with some amount of phosphorus, then gallium and nitrogen, nitride, then indium, some silicon carbide. There are some materials people have worked out very hard, and by properly mixing these materials, they are able to produce band gaps corresponding to visible light with different wavelengths. All these materials and in what proportion you are putting things, that will decide that the band gap is this much. So, you can have a component where the band gap corresponding to say 450 nanometers or 480 nanometers or 510 nanometers and so on, and properly if you mix all those things to make that PN junction, you can have a white light LED, and that is the crucial thing. That blue component was missing, and 214 Nobel Prize 2014 Nobel Prize was for this blue LED, you know that, blue light emitting diode. And after that white LED production became popular, and that is how we are in this era where everything is being all these our traditional sources are being replaced by these LEDs because of several advantages, the much lower power consumption and no warm up time, so no loss of heat there, no loss of energy there, and almost not very good monochromatic like a laser, but still that range you can tune. If you want to have a red LED, that wavelength range can be very small, can be say 50 nanometers, 60 nanometers and so on. So, you can have different advantages there, and you have all seen. I will just show you some of these diodes. This is a normal diode which is used for rectification or so. You can see it is a black thing in between, opaque from all sides, and then these two metallic contacts are there. So, this is our normal diode, no light coming out or no light going in. The band gap is much less than the photon energy. So, this is our usual normal PN junction. Then we have this photodiode. This is photodiode. In this photodiode, you see there is some transparent thing here. Okay, you have some pinkish thing, but then you can probably see a transparent window, so that light falls from outside, and then this junction can create current because of that and can measure this light intensity. Then you have this LED, the basic one single LED, not LED lamp. So, here this whole thing is a transparent cylindrical cap, and the top of that is like a hemisphere. So, this design of cylindrical transparent thing and top being hemispherical, that also has a significance. It concentrates light like a lens and then sends in proper direction through this top, and so these are the kinds of LEDs. We will be talking one more special purpose PN junction diode, and that is solar cell. So, the last example of special purpose PN junction diode will be our solar panel. This is also a very familiar object. You must have seen it at so many places on the building roofs and all those things. So, this solar panel is made of solar cells. It is a combination of different solar cells, and what a solar cell is, it is essentially a PN junction. So, solar cell, this is a PN junction. The structure is slightly different to suit this particular application. You have let us say you have this P type of silicon. Most of the these solar panels and cells are made from silicon, and on top of that a very thin layer of N type is deposited. So, this is N type and this is P type. So, you have this junction here, you have this junction here, and then the idea is to let light fall on it and create a voltage. So, the metal contacts are done in a special fashion. The back side is fine, that is full contact. On front side the contact is in the form of grids, a metal grid. So, this is that cross sectional view. If I take this cross section, it will be something like this, and then the grids are like these lines, and then they are connected here, and in between this is space, in between the space, this is space here, this is space here, light falls from this on this N, this is all N type, this is all N type. So, light falls in this area. The grid slightly obstructs, so that should not be large, and then light falls on this junction. And as it was in photodiode, this light energy h nu, if this is greater than Eg, then you have a chance of what you call EH pair generation. So, electron hole pairs are generated. Light should reach this depletion region. When you are letting the light fall, it should reach this depletion region Pn junction here, so that these EH pair electron hole pairs which are generated are swept away by the electric field. Which electric field? The field which is there across the junction, across the in the depletion region. So, as usual, if you have a P here, if you have a N here, and you have a depletion layer, and you have electric field in this direction, and if you do not put any battery, do not bias it and create EH pairs, through this light falling on the depletion region, what will happen? The electrons will be driven in the direction opposite to the field. So, electrons will go this way and these holes will go this way, and you will have a potential difference, a charge separation, a potential difference, and of course, recombination will be there, and in steady state no current will be there, but there will be a voltage because of these extra accumulated charges, and that will be an EMF, and that will depend on this intensity, at what rate you are creating this, at what rate you are generating these EH pairs, that will decide how much will be the voltage. So, for a typical case, the width of this N type here, the width of this N type here, this side, this is typically, let us say, something like a fraction of a micrometer. So, 0.3, 0.35 micrometers, and this side will be much larger, this will be say 300 micrometer or so. Then this N side is, this is N side and this is P side, remember. This is heavily doped and this P side is moderately doped. So, these are the structural parameters. This is how it is done. And then if you, for silicon, so typically for silicon, if you have this let us say a P type and N type, this is P type, this is N type and so on, and you do not connect anything and you shine light on this junction area. So, the voltage which is generated, which is now called as open circuit voltage. Why open circuit? Because we have not connected anything, we have not made any circuit. So, this is open circuit voltage. This voltage which appears between this side and this side, light is falling, remember, light is falling, and then the voltage which is appearing here, which is a result of recombination, new generations and all those things, some accumulation is there. So, that is typically let us say 0.06 volt or so. So, that is the maximum voltage, but if you connect this solar cell to a circuit, if you connect it to a circuit and you draw some current, so current will go this way, right, because this side is positive, this side is negative, this is my N side, this is my P side. So, the current will be driven, and when current is driven, then your voltage might change as it happens with any battery. And if you short circuit it, if this R is very small, is 0, you just connect it, then what the current that is given, maximum current, that maximum current which is hardly in milliampere range, okay, so very small current. So, that is known as short circuit current. That is known as short circuit current. So, in general you have some resistance here, and therefore, the voltage also changes little bit, and you can ask what is this IV characteristic. And if you draw that, if you put here say voltage here and current here, and the current which I am talking of is now current given by the cell, What does that mean? If you have this Pn junction here and this side is P, this side is N, the current given by this cell, that is the current I that we are plotting here, and then the voltage across this junction, voltage across this cell, that is V. So, this Vi characteristic we are plotting. And that is if you have a good solar cell, then this it slowly varies, but then later it goes very sharply, and this becomes your open circuit voltage. So, this part is your open circuit voltage, this one where the current is 0. Okay. So, this is your open circuit. Voltage. And if you plot the current through the cell, it will be just reversed. Generally, when we did our Pn junction, Vi characteristics and all those, what we plotted in this Vi characteristics was current through the junction. So, if you do that, then this should be plotted in the I will be negative, the direction will be different, and then you will plot it like if this is V, this is I, this plot should go like this. This plot should go like this in 4th quadrant. So, that is how this characteristic will look like. Now, a common solar panel that I showed here, this kind of panel. So, this will have large number of solar cells connected in series and in parallel, because each solar cell gives a very tiny current and a very small voltage. So, by proper combination of cells, these kind of panels are made. So, that is about Pn junction, and in the next lecture we will go for a new topic which is called transistors.